talk is by Irina Lomazova from HSE in Russia. Irina, can you share your screen?
Yes,
okay.
do you see it?
Yes, great.
Yeah, thank you very much. So this is a joint work with Vladimir Bashkin from Yaroslavl. But before I start the topic, I first wanted to thank the organizers and for organizing this nice event and for inviting me. And also, I would like to tell a few words about Boris Abramовich. For me, he's Boris Abramowitsch, of course. And so to say, I'm from Novosibirsk period of his life and work. And this is a photo of, I would say, a fantastic team in Institute of Mathematics in Novosibirsk. I was lucky to join. So it is from mid-70s. And so just I was lucky, of course, to have Boris Abramowitsch, my supervisor, both when doing undergraduate study and postgraduate study. So it was really unforgettable time. And for me, Boris Abramowitsch is just the teacher. And also, so just I would like to show another photo, and it is so just 20 years after he left Russia for Israel, and so now it is 20 years before we are celebrating his anniversary. And it is in Moscow, in Moscow State University, and this was an event so for 100th anniversary of Petr Novikov, his teacher. So there are such lifelines, I would say. So just to add just a few words, for me, the most impressive was, so just of course, I was listening to many courses and was talking much with Boris Abramowitsch. And so just he has a prominent ability of making complex stuff clear and natural and precise at the same time. And so just I think it was really remarkable. He was a prominent teacher. So well, now I'm switching to the topic of my talk, and it is about Petri nets. And to say, Boris Abramowitsch also, so just with him I was doing horse logic, and later he pointed me to this field as an interesting field to study, and that's also was very helpful actually. So one more thing from Boris Abramowitsch. So just I remember just well when I was to defend my diploma, he told me, so just you do not have much time. So explain the problem statement, and speaking about proofs, details, so it's not so important. So now I'll try to follow his advice as well. So just it is about Petri nets, and Petri nets is a kind of automata for distributed systems. And so just from mathematical point of view, they are also equivalent to vector addition systems. So just looking at this example, so we have a bipartite graph where we have circles which are local states, we have boxes for transitions, and arrows show causal dependencies, and the transition can fire, so it is, of course, it has behavior, dynamics. So when it has enough to say resources in all incoming places, and then it consumes these resources and produces resources to output places. Just to to tell here, for instance, for T1 to fire, so we do need 2 coins of 10 cents, and that's it. And so also 1 token. So we put tokens here to designate the number of resources. 1 tokens in shop, meaning that shop is ready to sell it. And here we have also names for transitions. So all transitions T1, T2, and T3 are different variants for buying goods for 20 cents. So just an external observer seems just transition B firing. So we use labels to fire observable behavior of this system. So for this Petri net, of course, it is easy to see that one more word, so one more sentence, is to say that a state is a distribution of tokens, and it is clear that 1 10-cent coin is equivalent to 2 5-cent coins. We know that from everyday life, but here, of course, so we can't buy anything for 10 cents, we do need 20, but we can change 10 cents for 2 coins of 5 cents in any marking in any state. So that's the intuitive idea under these resource equivalences. So we would like to find a way for so finding equivalent resources for given Petri net. What for? So this it can be helpful because we can use them for state space reduction, for Petri net reduction, also for adaptive control when we can change so some resources in the course of the run of the process by another for process optimization. So just it is clear that though it is a purely mathematical problem, it may be used in application. So this is just for Petri net notation. So we have a state, which is a distribution of tokens. That means that we have a multi-set of places, local states. That's a global state to say. We have transitions, and we have labeling functions giving names to transitions. The notion of dissimulation is very general, of course, and so just it can be applied for to Petri nets as well. And 2 markings are considered equivalent if they generate the same observable behavior. Formally, it can be defined with the help of so-called transfer property. So it looks like following. So just we have a relation on markings, and if so we say that M1 and M2 are equivalent, yes, connected with this relation. If we can fire transition T here, then we can answer, so imitate here with another transition with the same label. So it looks like the same action occurs, and we come to also 2 states related with the same relation M. So we have this transfer property, which shows actually that one process can imitate the other, and we call a relation a marking dissimulation if both, so it is the same relation, both this relation and its inverse relation satisfies the transfer property. That's a nice thing to study, but there is a bad news for Petri nets. So it was proved by Petri that marking bissimilation is undecidable for Petri nets. There was another equivalence relation studied before, which is called place fusion. It was studied by Philip Schnoebelen and Natalia Sidorova. And so just intuitively, it means that so we can, in any reachable marking, we can replace a token in one place by a token in another place. Then we say that these two places are equivalent and we can fuse these places and then in some sense optimize our system. But bad news, place fusion is also undecidable. So still, just I didn't show this in the slide, but so it is known that there is that Bisimilarity is decidable for a very restricted class of Petri nets where each transition has exactly one input arc. And in this case, so this equivalence is also a congruence, and that's very important for decidability. So what can be done? We can try to consider congruent narrowing of our equivalence. So then we say that two resources are similar if replacing one of them by another in any reachable marking does not change observable net behavior. It means that if we substitute one resource instead of another, we get dissimilar marking. So resource similarity can be easily defined, and it can be shown also easily that so resource similarity, of course, if two markings are resource similar, they are bisimilar markings. So it is a narrowing. And also it can be easily shown that it is, to say, strictly included in bisimilarity. So we may easily construct a net when we have the two markings are bisimilar, but they are not resource similar. So we still have bad news that resource similarity is undecidable, and it immediately follows from the result by Schnoebelen and Sidorova, because so resource place fusion is a special case of resource similarity. Still, resource similarity is an interesting relation because there are good news that resource similarity can be represented, so has a finite description, can be represented with finite means. So it has some nice properties. So resource similarity is closed under transitivity, it is equivalence, it is closed under addition of resources, addition of multisets, and because it is a congruence. And so then it can be proved that this relation has a finite additive transitive basis. So just I'll skip these details, but just, of course, I will not read this, but I just tell that for Petri net theory, well, quasi-ordering, but not only for Petri nets, can, of course, so are very helpful. And for instance, a well-known technique of covariability tree for checking boundedness of Petri nets is based on well, quasi-ordering. So here we can define a different quasi-ordering, which helps us with similarity. And with this quasi-ordering, this finite additive transitive basis is exactly the finite set of minimal with respect to these ordering elements, minimal pairs. So we know that there exists a finite basis, but we know also that we can't compute it, because if we could, then we can, of course, also check effectively whether two resources are similar or not. So bad news is resource similarity is undecidable, so we look for maybe even more restrictive equivalence, which will be a subset of Bisimilarity relation, and for which we can compute something. So we define one more equivalence, which is called resource bisimilation. And it is this is the definition. It says that our relation is a resource bisimilation if its additive transitive closure is a marking bisimilation. We know that each resource bisimilation is a marking bisimilation, of course, and then so should be a marking bisimilation. And then so we know that it should be closed on transitivity. It is an equivalence and addition for congruence, because we would like to substitute it one resource for another. Then we can check so similar properties for resource bisimilarity, and we have that, yes, so just we can, so this was resource bisimilation, sorry. So that resource bisimilarity, maximal resource bisimilation can be defined, and that we have that it is a narrowing of resource similarity, so it is more strict. Also similar to as it was done for resource similarity, we can prove that resource bisimilarity is finitely based. So each resource bisimilation has a finite ground, so from, meaning from minimal element with respect to our ordering elements, and it is an additive transitive basis. So just also the maximal resource bisimilarity also has such a basis, and it is finite. One more characteristic property of resource bisimilation is a so-called weak transfer property. This property was defined for place fusion and for place bisimilation, yes. And here it is generalized for general notion of resources. And the difference is here, you see, so just we also construct a diagram which describes how to mimic one behavior with another from one state to another. But here, when we want to fire something, we can add resources we need. So just we can't fire from R, then we add everything what is needed to fire T, and we add it also for another one. So then it is actually that we can mimic it in any environment, in any resource environment, and then of course we can suppose that it is what we do really want. So that's it, and it is proved that this is a characterization of resource bisimilarity. So a relation on resources is a resource bisimilation if and only if it is an equivalence and it satisfies the weak transfer property. So then we have three relations: marking bissimilation, resource similarity, and resource bisimilarity. And we have that for if we have a resource similarity, then it is a congruence, of course, and it strengthens the marking bisimilarity. If it is a resource bissimilation, it's a marking bissimilation, and so just its additive transitive closure is a marking bissimilation and also a congruence. So how to compare these three equivalents? We know inclusion, but so it's interesting whether this inclusion is strict or not. So I mentioned already conflict-free Petri nets, for which marking bissimilation is decidable. And for this class of Petri nets, rather restricted, we have that all three relations coincide. For general classical Petri nets, we have that, of course, marking bisimilarity and resource similarity do not coincide. That's easy. But what was not known before, so what about resource similarity and resource bisimilarity? So we show that here also we have strict inclusion. And I can show an example of a Petri net for which we have two resources which are similar but not dissimilar. So we have resource similarity but not resource bisimilarity. So this gives us a chance for proving that resource bisimilarity is decidable. And to explain these specifics, so just we can use the notion of resource bisimilarity game. So just people who work with state bisimilarity know this bisimilarity game. It is a classical construction. So here, similar to this classical game, we define the game, but the difference is that, so just when we have attacker and defender, and the attacker tries to show that two resources are not equivalent, and defender, of course, tries not to allow him doing it. And then, so just when attacker fires a transition, then he can add resources needed for firing this transition. So he can fire any transition for any resource. So adding something, and then this addition can be used also by the defender. We define such game, and we have a statement similar to the classical statement on bisimilarity game, which says that for if we have equivalent pair, then the defender has a universal winning strategy, and if they are not equivalent, attacker has a universal winning strategy. So just I'm afraid I didn't say that. So the winning strategy for attacker is to come to so just around when defender can't answer to his attack, and for defender it is just an infinite game. And then, so just we consider the problem of resource dissimilarity, which sounds that, so we have a labeled Petri net, we have two resources, and we would like to check whether they are dissimilar. And good news here is that resource dissimilarity is decidable. The algorithm for checking resource dissimilarity uses, so just is based, uses also the well-known tableau technique, which should be adapted actually to this special case. So of course you can't just so just use it everywhere. For similarity, it doesn't work at all. But here So we can use this special well-fuzzy ordering and some other properties of dissimilarity. And the idea is that a proof tree is constructed, and this proof tree is finite, and there are finitely many such proof trees. So this proof tree is, in some sense, is a condensed finite version of the winning strategy for defender. For attacker, so his winning strategy, if it exists, so is always finite, but for defender, it is generally speaking infinite. So, but in some sense, of course, it would be very, so to say, so just not precise and concise, but actually, in some sense, it is similar to coverability tree construction, when we have this possibility to have a finite variant of reachability tree, which is enough for proving what do we want. And here is the same case. Returning to the example when we have that two resources are similar but not dissimilar, the point is that so just it could be that so in any resource environment, two resources give the same behavior, but to prove it, there is no universal technique. So for different environments, we have different strategies. If we have one strategy, it can be encoded in this proof tree, and then this problem becomes decided. So that's the difference. And we have cases when, so we have resource similarity, but there is no way to prove it. So just 2 minutes more to say what remains an open problem. So we know that resource dissimilarity is decidable, but we would like to know how to construct it finite at additive transitive basis, because well, so just we can check dissimilarity for two concrete resources, but if we know how to construct this finite basis, we know the entire relation at once here. So for that, we know that first weak transfer property, of course, can be directly verified for finite relation, and we can approximate it. So just we can consider only resources of size 1, so meaning multi-sets of size 1, 2, and so on. And then we have this inclusion. And of course, since there is a finite basis, we have some limit. So such a number, when we have this, when we compute our resource dissimilarity for resources not greater than this size, and then we get the complete relation. But so just it is not clear how to compute it, and it is an open problem. I skip it. So I come to conclusions. So we've discussed resource equivalences, and they are resource similarity and resource dissimilarity. Both are equivalences, both are congruences, both are finitely based, but the first is undecidable and the second is decidable, and the second is a strict sub-relation of the first. So approximations can be effectively computed, and the open problem is to compute the size of additive transitive basis. So further research, of course, there are many ways to continue it. So just I think it's time to stop for me now. Thank you very much.
Thank you very much, Irina. Any questions here or on Zoom? One thing we're wondering is the complexity of the decision procedure, if you know some lower bound.
I do not know exact, of course, estimation. So I think it is really very high exponential to say. But what we did together with my student, so just he implemented this algorithm. And then, so we got what we have suspected, that when, of course, we consider, so it, the complexity depends on the size of resources, not on the size of the Petri net. So just if resources are not really large, then we can compute it. And then, of course, there is a body after which, so now they compute it, at least so just available to us, can deal with it. So just, of course, it is expected, but also it gives some so hope, since so we can do it for large nets, for large systems, but we can look for small resources which can be changed one by another.
Okay, thank you.